Hi everyone, welcome to our event. This event is brought to you by Data Talks Club, which is a community of people who love data. We have weekly events, and this is one of such events. If you want to find out more about the events we have a link in the description. Click on this link and you'll see all the events we have in our schedule. Do not forget to subscribe to our channel if you haven't for some reasons. This way you will see all our new videos in your YouTube feed. And then finally, the most important thing, join our Slack to hang out with other data enthusiasts. During today's presentation, you can ask any question you want, and then at the end of the presentation, we will cover these questions. So with that, I think it's all from my side. And now, Jeanine, the floor is yours.
Thanks a lot, Alexi. Thanks a lot for inviting me as well. I'm going to share my screen. I hope it works.
Usually you ask questions during our webinars, but today it's different. So yeah, thanks a lot for agreeing.
Well, thanks a lot for inviting me. Is it okay for the screen?
Yes, I can see it.
Okay, perfect. Well, thank you everyone for joining. Today I'll be talking about productionizing a feature store for fraud detection at Ubisoft. So Ubisoft is a French video game company with development studios across the world. I suppose you've heard about it already, thanks to Assassin's Creed, Far Cry, Just Dance, any of these games should be a trigger for you about Ubisoft. But today I won't be talking about games. So let me first start by introducing myself. So at work, my name is Jeanine Harb. At work, I'm a machine learning data engineer with a background in software engineering. And I've been a data engineer at Ubisoft since 2020. I joined right before the pandemic. And my main focus is applying best practices of software development to data engineering because of my background as a software engineer. It was my first diploma. And then, and also I work on data pipelines, engineering them, making sure they work correctly in a robust way. Also applying MLOps and DataOps to our machine learning projects. And also on the side of my technical activities, I also organize data-related events within Ubisoft Data Office. So the Data Office is the entity at Ubisoft which gathers all the data teams. Outside of work, I really like modern art. I also participate to acquire. I love indoor gardening, and I'm a trained facilitator of I Am Remarkable for workshops. So it's an initiative to empower women and underrepresented groups to celebrate their achievements at the workplace and beyond. But today I'll be talking about my main activity, which is being a data engineer at Ubisoft. And I work on a project that handles fraud detection. So let me tell you a bit more about how we do fraud detection at Ubisoft. So why first? Why do we do fraud detection? It's because we are handling 20 million of transactions per year on Ubisoft's e-commerce platform. However, we face fraud attacks regularly, mostly through reseller websites that try to buy Ubisoft products using stolen credit cards. So we try to fight this kind of abusive behavior because it could degrade Ubisoft's reputation among payment providers as well as players, and it incurs money loss as well as bank fees for Ubisoft. So it's important for us to create a shield in order to defend ourselves against these kinds of fraud attacks. We used to fight frauds thanks to an external solution, which was kind of an expert system where we defined several rules based on conditions, and it would be human-defined, so there's no automation whatsoever behind it. This external solution rejects a transaction based on these rules that are defined. However, this solution has some limitations. Some of them are related to data richness, so we cannot compute all the behaviors that we want to monitor in our rules. Also, fraud patterns are humanly detected, so they're non-exhaustive. They could lead to, like if fraud patterns evolve, we could miss them because we have to be there or we have to think about it in order to be able to detect them. So there's no automation. and also the cost. It costs us a lot without necessarily having a very good ROI. So that's why we decided to try and implement something ourselves. What about now? Now we are using Omni, which is a Ubisoft data office project. So we developed it internally, designed to detect fraud on e-commerce transactions by using machine learning models and applying feature engineering on user data. How does it work? So let's say we have Einstein who would like to buy the deluxe pack that costs 99 euros, but Einstein feels it's a bit expensive, you know. So Einstein goes on the reseller website, which advertises for the same product at a lesser price, 25 euros. That's a nice discount. But in return, Einstein needs to provide his Ubisoft email, his password, give access to his account, and deactivate the two-factor authentication that allows us to know that it's Einstein who's doing the transaction. And the reseller, once paid this 25 euro fee, does not actually use the money Einstein paid, but uses a stolen credit card to buy the product on Ubisoft's e-commerce platform. At this point, for us, we implemented some kind of module that intervenes when the transaction is being made on the e-commerce platform. And this module is based on a machine learning model that consults historical data related to the user Einstein. So in this case, our model sees that it's a 2-year-old account. Okay, fine. But there were some password resets in the past 14 days, so around 4, which is a bit suspicious. Also, the playing country is different than the buying country. And of course, here it's a very simple example to explain to you how it works. But based on these suspicious behaviors, the machine learning model is trained to recognize that there's some part of fraudulent behavior that could be seen here, and would advise to reject the transaction. So this is how it works. The machine learning model emits a score, and based on that score, we have a probability of knowing whether the transaction is deemed fraudulent or not. In that case, as you can see, we heavily rely on historical data, on user data, to calculate this risk score in order to efficiently detect fraud in real time. Scope of this talk. Let me tell you a bit about what I would like to talk about today, but mostly this is not about techniques for combating fraud on e-commerce platforms. I'm not an expert in that. Also, it's not related to how to train the best machine learning models for fraud detection. There are countless papers on the topic. We're not gonna go deep into how to handle imbalanced data or how to monitor KPIs related to ML products, or how to work on how to design the infrastructure in such a way that it works with a high volume of data. So definitely this is not a corporate expose on state-of-the-art implementation for fraud detection. But you might ask, what is this talk about? It is about how we leveraged feature engineering for fraud detection. So today I'm just going to be talking about data, and a lot of data, and how we design a feature store, with something that I'm going to introduce a bit later on, that interfaces with training and inference environments for machine learning. How we applied best practices of software engineering to data engineering. Also, how we view data as code. So this is definitely a personal take on my collaborative work as part of my team. And I'll be sharing with you today our data engineering journey and the challenges we faced along the way. First, let's talk some definitions. What's a feature store? You might ask, but first I'm going to explain what's a feature, because that's an important part in understanding what a feature store is. In our case, in this talk, a feature is an indicator. It's a characteristic of the phenomenon that we want to observe. We would like to observe patterns of fraud. So we want to create indicators or aggregations, calculations that could explain or describe an aspect of a transaction that can serve later on to identify if it's a fraud or not. For example, a feature that's very efficient in detecting fraud detection is the geographic gap. In Ubisoft, we organize countries as business territories. And let's say you have US and you have France, and then the business territories are different. So what we try to compute on the left side of the slide is the match between the business territory of playing, where the user usually plays, and the business territory of buying, where the transaction was made. We've noticed that 90% of fraudulent transactions show that the business territory are different. So this is, for example, a feature that can explain 90% of the frauds that we see on the time interval written here. Other types of very significant features, we have the fraud history. So how many times a user has frauded in the last 12 months? You would, like, it would seem logical for you to say that a person who has frauded 5 times in the past year could fraud again. So this is a very important feature for us. Another important feature is the number of transactions made in the last 5 minutes. So this could allow us to detect spammers, for example. Another example is the deactivation of the 2FA. How many times has it been done recently? We saw that this deactivation is very important for reseller platforms. So this here, the feature allows us to reproduce all the insight that is accumulated by fraud experts over time, but in a mathematical way. And we're trying to speak the language of a machine learning model, which is through numbers, through statistics. So what does it look like in practice? In practice, we would calculate these features that I talked about early on. We would calculate them for each transaction. So let's say the transaction 1 made by Albert Einstein that cost 99 euros. The buying country was in the US, but usually Einstein plays in France. So we are able to calculate the following 3 features: the number of reset passwords in the past 14 days, 4, that's high. A gap in business territory, it exists. Also, we can check the fraud ratio per country. So this is just an example, but for example, here everything indicates that Albert Einstein might be a fraudster. So we would block it. This here is an example of a feature store. So it would mean that we would create some sort of a table of a store where we would put all the transactions, the elements that we want to observe, calculate the features that correspond, and try and feed that to a machine learning model. A feature store is a very important element in data engineering for such use cases, because it allows us to regroup all the data sources and apply consistent transformations on them. So a data scientist does not need to create his or her features on their own. They could create them as part of the feature store, and then they would be centralized for all the team to use and for other teams to use as well. The benefits of having a feature store is that your code is aligned, it's tested, it's also validated and monitored through processes that you can put in place. And so it creates a single point of truth for model training as well as inference in real time. When we talk about feature stores, we also talk about online and offline feature store. The online is when we compute the features in real time for model serving. The offline is when we compute the features on historical data. So when we take, in our case, all the transactions and we calculate all the features across them, and then we feed this table to a machine learning model for training. So now that we set the basics, let me tell you about our journey, how we implemented the feature store as part of Omni. So our project started in April 2018 when some data scientists from our team wanted to find a way to leverage machine learning models on business use cases at Ubisoft. So it seemed that fraud detection was a good use case. So they discussed with experts, they tried to come up with an idea, a proof of concept was launched, and then Omni API was deployed with a first version of a feature store in January 2020. So this proof of concept was implemented this way. So as you can see, we have the offline on top for model training. We have also another pipeline for the online feature store for inference. And each one of them requires different processing to create it. So we see that we have implemented some SQL scripts for the offline part that gather historical transaction data with coupled with transaction data, contextual data, and this computes all the features for the offline part. But on the online part, since we work in a different environment, we're inside the e-commerce platform, so we have to follow the architecture that was already put in place. We're on AWS in a Python environment, and we are using live transaction as the main source of data. We couple that with contextual data. We calculate the features in Python, and we create the online feature store. So this was great for the initial proof of concept because it allowed us to show the project's full potential really quickly. It allowed us to implement ideas, to test features, to see how it would work in real life. However, it had some cons, of course. So after examining the script on the offline part, we noticed that the implementation was not optimized at all. There was a lot of cross joins. There was no code versioning. It was super complicated to maintain. Every time we had a bug, we had to go through the entire script. And believe me, it was way too long. So readability was not great. It was always a pain to try to go back to the main source of the bug. Also, we were recomputing the offline feature store from scratch every day, so big volumes of data, which meant a lot of processing, a lot of long execution time, so we could not iterate quickly. Any seasoned data engineer would notice that we have a big split between the offline and the online execution in this design. So there was no code alignment at all. The code that was executing the online features was quite different from the offline. On the offline side, we had declarative SQL that doesn't run the same way in Python. So we had shifting definitions because we defined features in two places differently. So any maintenance we would do on one side, we had to do it on the other side in a different way, which meant human error, which meant bugs, which meant discrepancies. So it was not a great option for us. We needed to find another design to make it prod ready. At this point, we started research for a feature store V2 design, but at the same time, we had a bit of time constraints, so we had to come up with a more optimized version of the feature store V1 in the meantime in order to keep the pipeline going. So that's what we call the feature store V1.5. The difference in the feature store V1.5 relies in the offline part only. So we converted the SQL scripts into PySpark SQL, and we took this as an occasion to optimize the SQL operations. We removed the cross joins, we optimized the I/O, we used some partitioning, some checkpointing to make it easier to reuse the data. We versioned the code, very important here. And also we moved to a design where we tried to generate the feature store a bit more incrementally. So we did not have this batch regeneration, this full regeneration every day. We moved to a more batch way of creating the data. So it was still a bit complicated to maintain because we still had some kind of disassembled scripts that were a bit still long. We had some duplicate code, and we did not have any tests. Also, we did not solve the issue in the code alignment between online and offline, but this was, I'd say, by design, because we knew that a new design was coming with the Feature Store v2. So Feature Store v1.5 was some sort of a big house of cards, and it proved the adage that proof of concept are not meant to last, because every time we were trying to change something, to add something new, we would end up with even more bugs, and we would not know how to go through them or how to fix them correctly. So it was very clear to us that we needed to move to something better. And that's where we started R&D on Feature Store v2. We started like implementing whatever we saw during our research phase and tried to come up with a new and improved design. We were motivated by several design considerations, 3 of them actually. The first one is that we wanted to keep the incremental part. It was really a good move for us because it implied less daily processing, less data shuffling, and so we could iterate quickly and generate the data more quickly. We also wanted a unique pipeline that catered to both training and inference, because it meant that we wouldn't have any code duplication, and we would be able to actually test whatever we create. And finally, code alignment. We need to define a feature once and find a way to make it run in both environments. So that would mean that we wouldn't have any human errors during regarding maintenance. We wouldn't have any like, if we test the code, we're sure that it works. And also, if we want to change it, there's only one place to do so, and we could add features more easily. So this is what drove our concept for the Feature Store v2, and we ended up with a different architecture. Of course, this is very high level. It's not detailed enough, but this is just to show you the concept behind it. So as you can see, we still have our model training and inference, which is normal to have it separate because we have different data sources for each side. But the main pipeline that caters to both environments is unique. So what happens first? We added a new step called batch processing. It serves like a pre-aggregation step, some sort of a pre-processing step for the data to gather all the historical transactions, all the contextual data, and create a user history, a table that would gather all the users' history in a very simplified format that can work for both environments. In this design, the user history was aggregated thanks to complex types. So we would create, for example, an array of date time for password resets for a same user. We'd also create a dictionary of date time coupled with the transaction amounts to create the transactional history. So here we keep only the data that's interesting for us. We reorganize it in a way that's also easy to read, to feed to our library, and then we would have some sort of a unique data set that caters to the feature calculation. For the feature calculation part, we ended up with a library where we would implement all of our features, and this library would be used across both environments. So what happens, for example, in the library is that we take the array of date time for password reset, and we can calculate the number of password reset of this action on the past 14 days. The feature becomes a function that has an input from the user history. It has an input as well from the transaction data, be it historical or live, and computes the feature for offline or online use. Why did we implement this additional step here? It's because it created the same base for end feature calculations, and it allowed us to align historical data between online and offline. So what happens is that on online, we cannot, it's a Python environment, so we cannot really use any group bys or joins as we can see in SQL. So by having these arrays here, we avoid using costly operations and having to create a Spark environment on in inference time. Also, you might ask, how can the library be called in two different environments if we have such like a different way of a different infrastructure, I'd say. It's because we decided that the features will be implemented in Python, so that's easy enough for the data scientists to implement them because it's a language that they use in their day-to-day work. And online, nothing changes. We import the library and we can call the features natively in a Python environment. As for the offline part, we leverage Spark's user-defined function interface. So these UDFs take any Python code and transform it in such a way that it can run in a Spark environment. So since the data is pre-aggregated in arrays, we do not have any performance issues on that end. As to the data access, we implemented an abstraction that can allow us to read from different data sources, depending on the execution environment. So if I take a short snippet of the code, I can show you, for example, here, how we can implement a feature. So a feature is a Python class that's instantiated. It has a name, it has a description, so that's your documentation here. You have the data type, which is important for validation. You also have the feature implementation in that looks like that is a Python function actually that you can import and use. So here the function is called total amount last X minutes because it's parameterized, so we can use it for many use cases, not only over the last year as the feature is defined here. Also, we define where to go get the data depending on the execution environment. So the platform, which is online, we can go find the data in the JSON payload that contains the information about the transaction. So we have the transaction date, we have the transaction list that is enriched in the payload thanks to the user history. On the training side, so that's the offline part, the data is in Parquet files, it's Spark data frames. So we would give the name of the columns that holds the required information. As the feature implementation is a Python function that can have many parameters, we can also configure the parameters here. So as you can see, we've converted the number of the amount of years into a number of minutes, and this here can be just we can define 5 minutes, we can put an hour or several days. So it can depend on whatever we want from the feature. And finally, we can have a feature default value because the model does not work well with null values. So in case we don't have the information, we default. As you can see, documentation is embedded in the code. So we only need to look at the feature to know what it does, how it's calculated, how it's parameterized. So there isn't there's only one-stop shop for feature definition. And this feature, as defined here, can be used, be it online or offline. The code can also be reused. As you can see in the feature implementation, the name of the function indicates that it can be used for several amount of times. The code, we designed it to be modular, and since everything is a class, it's a function, so it can be unit tested very easily and can run everywhere. And by here, I mean, can run online and offline as well, in a Python environment and in a PySpark environment. In order to put the feature store v2 in prod, not only did we design the features as a library, we also implemented a lot of best practices regarding software engineering. We created unit tests for everything, for all the features, all the environments, using all the data sources. Everything was tested carefully. We created a dual run mode where our implementation was running in shadow to compare performances with any previous implementation and make sure we don't drift. We did as well some data quality checks. We checked the freshness, the consistency, the completeness, the constraints of the features. For example, a feature that calculates the sum of amount over the last year cannot be negative. So this is something that we test. It's important to not only to test the code, but also to test the data and make sure that what you're producing is correct. Since we have two different environments, we also implemented monitoring for both environments, for all the pipelines and the automation that cater to them, all the flows. We check the data freshness to make sure that we have up-to-date data. Also, we monitored the performance. This is something very important, is to make sure that the model still works accurately with the new data that we're providing it with. So we worked with our data scientists and machine learning engineers. We worked with our project owner to make sure that the accuracy doesn't drop, that the false positive rate is also good, and that the business KPIs are still maintained. And finally, we implemented all necessary automation for continuous delivery, which allows us to iterate very quickly on the code. And anytime we want to introduce a fix or a new feature, we can do it like we would do in any other software engineering project. Thanks to all of this, the Feature Store V2 now runs in prod as of 23rd of February. So we're super proud of that. That was a real achievement for our team, because all of us, like I'd say, yeah, the entire team worked on it. So kudos to the entire team. And this here is a team appreciation slide. Thank you all. That was when we celebrated the Feature Store V2 and prod. So really, it's an honor to work with you, everybody, and this is a real team effort. Thank you. So some final thoughts and some FAQ before we go there. You would ask me what's next for Omni's Feature Store. I'd say a lot. Our new design is, of course, not perfect, so we always aim on improving it constantly. But we want to improve the continuous delivery lifecycle, make sure that we have consistent versioning of the code as well as the data. We would love to decouple the use case from the architecture to be able to inner source our feature store across other projects within Ubisoft. And of course, follow best practices on using incremental data formats for source data. We would love to add more features, to participate in R&D, be it on feature engineering or new data models, and aim for even more and better automation of our flows. And if you feel that our feature store implementation looks familiar, it might be true, because we're not the only ones implementing features as code. There are several open source libraries and proprietary feature store platforms that have also found that this design, this architecture for the code works well. For us, this is a measure of success, because it means that we converged on a design that seems to be convincing for practitioners in the field. So for us, this sounds great. Does it mean that we will abandon our implementation and use a more established feature store library? I'd say not yet, because we've been closely following all feature store initiatives, and there are a lot of promising options, but still we cannot really say that there is one established feature store library for now. But for the moment being, our implementation is quite tailored to our needs. It allows us to compute features using a unique implementation on different data sources. And this is something that we haven't really observed yet. But of course, if anybody in the audience has some suggestions, feel free to send them in Slido. What I wanted to end with is that in all machine learning projects, we can quickly go in a way that doesn't allow us to go in prod. And I'm not the one saying that. This paper from Dee Scully at Google talks about hidden technical debt in machine learning systems. It's quite it's well known, this paper. I really love it. And as you can see, there's this small little box, black box in the middle that talks about the machine learning model, the ML code. But all around is the entire ecosystem that needs to be handled before we can ship to prod and before we can have a project that is valid and robust enough. And most of it requires data. So data is a really very important aspect of everything we're creating, and we need to design for data. That's why, in my opinion, we need to treat data as we would treat code. So it's very important to keep in mind that the best practices that we have in software engineering can also apply to data products. So in this case, we could have versioning, CI/CD, unit test, documentation. We could have data quality checks, monitoring, performance reviews. And all of it is super important for us to ship into prod, to have something that's robust, that's scalable enough, and that we can iterate on, and that is valid. And that's what's important in machine learning, I guess, is having a valid result for the use case that we are looking to solve. So this is all for me. Thank you all for listening. I'm looking forward to your questions.
Yeah, thanks a lot. That was quite packed with information. I do have a few questions. Maybe you stopped sharing your screen too early because I wanted to ask you about the architecture. One of the slides where you show this V2 feature store. Maybe you mentioned that, I just don't remember. What kind of database you use for online serving? So for offline, as I understood, everything is in Parquet, right? So you just and for online?
Yeah, I didn't mention it, but we use a DynamoDB. So we load some of our features in DynamoDB. We load a bit of the history data there as well. So it's a highly available database that caters well to real-time use cases. So on our end, we really need to answer in near real time for the transaction, for the prod check. So DynamoDB is a very good tool for that.
Yeah, for a similar use case that we have to Elixir for also fraud detection. Well, we don't have like a feature store, but this is something similar. So we calculate features online, and we also use DynamoDB for that. So it's pretty cool. One other thing I wanted to ask you is so you have these features that you compute. It's sort of a running window, right? So up to this point, how many like it's like a counter up to this point, how many times I've seen this event happening, right? It's how many times like the user changed the password, how many transactions were made. And I'm wondering, because you're running these things as batches, right? So you're calculating features in the batch mode, right? And then the data goes to Dynamo after you recalculate them, right?
Well, actually, we send the arrays that we pre-compute. We send them to the platform, so they are in DynamoDB as well. So we don't pre-compute the counters because it highly depends on the date of the transaction. So one thing that we struggled with is having out of date features because they were pre-computed, but then 24 or 48 hours happened and then they were not up to date enough. So that's why we opted not to pre-compute, to wait for a transaction to happen and then to compute in live. But for that end, we need to pre-aggregate the data to make sure that it's optimized, that we don't need to do any kind of costly operation before on the spot.
Yeah, that's the same problem we have with the system I just mentioned with putting things to Dynamo. And I'm wondering, so let's say I just made a transaction, right? And one of the features is number of transactions that happened over the last year, right? This is one of the features you have. So if I just made a transaction and then now I'm making another one, how soon will they have an updated counter for the next transaction? Is it immediate or there's some delay between the two events?
There's a tiny bit of delay because we update our database in near real time. So we have like a few minutes delay in our database, but we're aiming on improving that. So that we constantly have new flows and new mechanisms to update the data online. And the data offline, it's not necessarily we don't necessarily need to have it that quickly. So we wait for it consolidated in the enterprise data platform, but for the online part, that's where we try to be in near real time. Yeah.
So as I understood correctly, then that you are doing some sort of mini batches, like you run your batch job like every minute or every 30 seconds.
Yeah, that's it.
Okay, and then it puts the data to Dynamo, and then from there, in real time, when you get a new event, like let's say a transaction, and then you go to the feature store to Dynamo, you fetch the values, and then you run the model.
Exactly.
Okay, thanks. Let me share my screen. There are quite a few questions. So question from Slava. Do you have data feature versioning in the feature store?
That's a great question. That's one of our next topics to handle. We have some kind of a feature versioning. I'd say it's part of the code, so it's versioned, but it's not as granular as we'd like it to be. So there's a whole discussion going on right now to see how best to version our data. If we need to do data versioning for every patch, every minor version, or every major version only. So data can be a bit more tricky, but because it involves a huge volume. So if we want to version, it would mean that we would replicate our data and our processes for each version. So I'd say we don't have a clear answer yet for the moment, but this is something we're definitely working on.
And I'm wondering what would be the use case for, let's say, if we talk about fraud detection. One thing would be if you want to sort of travel back in time to retrain your model on some data from the past, right?
Yeah,
apart from that,
it could also be for comparing versions, actually, because if you have some new feature, or even if the data source has changed, you would like to go back to maybe to make sure that you really corrected the bug that you were encountering, or you've correctly added the new feature. So I'd say it's mostly to compare consecutive versions. I don't know if you would keep entire histories of versions for that end.
Yeah, thank you. Another one, for the online feature store, wouldn't you need the latest data? But job does not guarantee this. How do you ensure data in the offline feature store is the latest? I think this is what we talked briefly, right?
Yeah, definitely. We update the DynamoDB with the latest data.
Do you want to add anything to what we already talked about, or?
Well, for me, it's a kind of like a stream job. So we have that gets the latest data that feeds to the DynamoDB, and then the data is updated in the for the payload for the feature calculation. So yeah, we keep this log of recent transactions on the online side.
It is not clear to me how the feature store is used after models are trained. The online feature store. Can you explain that a bit, please?
Is used after.
Do you want to share your screen?
I don't have any supporting document for that, but for the online part. So actually, we are giving the features to the model for inference. So instead of giving a table for training on the offline side, we would just provide the features for the current transaction on the online side, and then we have a SageMaker endpoint for that. So the model is hooked on a SageMaker endpoint that gets the features and then provides with a prediction.
So I imagine the way it happens, you get an event, right? This event is, let's say, a transaction. And then you get, maybe you have some transaction ID, you have some user ID there, right? And then for these IDs, you fetch the information from the feature store, right? So then you get the values, and then you send these values to SageMaker endpoint, right? And then in the endpoint, you have the model, then the model replies with some prediction, and then based on this prediction, you decide what you want to do. Like, do you want to look closer at this transaction, or it's fine, right?
Yeah, definitely. So yeah, everything happens in the Lambda that calls the feature calculation. So we call our so we get the payload as a JSON in a JSON format. The payload is actually the transaction. We enrich it with the user data based on the user ID, as you said, from the DynamoDB. We feed that to the feature calculation library, and once we get all the features, we send the entire feature and transaction to the model, to the SageMaker endpoint, and then we get the score.
And there's a related question I see in live chat is, are you still using Lambda in the feature store version 2? And I think you just answered that you do use, so a payload, the event is processed by the Lambda function, right?
Yeah, definitely. Yeah, I did not really go deep into that because that part did not really change across feature store versions. It's mostly all the feature engineering part that was really rethought and redesigned.
What do you use for these events? Is it Kinesis or SQS or something like that?
Yeah.
Sorry, what?
It's the SQS, indeed.
SQS. Okay.
Yeah.
And then so you have a Lambda that is connected to SQS. So something puts the events to SQS, Lambda pulls them, scores the transactions, and then saves the result somewhere, right?
Exactly.
Computing features at inference time when a transaction happens seems to be not standard across feature store solutions, I found. Is it an issue you share?
Indeed, this is why we did not jump on any other feature store implementation that we saw out there. It's the main difference actually is that we have a very different data source on inference time, but that needs to be computed with the same code. So this is why we re-engineered our feature store around that in order to align the implementation as on training and in inference time. But still while having different data sources.
So Dynamo's DB maximum record size is 400 kilobytes. Was it ever an issue for you?
Yeah, I'm quite. this makes me smile because we struggled with that for like a month at least. So yeah, indeed, it was an issue, and we had to try to find ways around it. And how and one of the ideas that we had is to limit our history to 1 year. Actually, all our features work on 1 year maximum. So this way, we would limit the amount of data that we would feed into DynamoDB. We also reduced the element names, for example. We tried a lot of things to reduce the data in such a way that we could stay underneath this 400 kilobyte maximum size. But indeed, it's still. This is, I'd say, this is why it's not a perfect implementation yet. Is that we didn't really solve all the issues that we could encounter. So having these arrays has its pros. So it's, for example, it's aggregating the entire user history in an easy way, and being able to have the most up-to-date data without aggregating so much as to lose the freshness of the data. But on the downside is that we have to struggle with the volume of the data that we accumulate. So there's always a trade-off.
Yeah. Another issue with DynamoDB I remember is configuring these read-write patterns. Like, do you go with provisioned access or do you go with on-demand scaling up and down? So I remember, so for us, it took a bit of trial and error setting this up.
Of course, us too.
Okay. Do you backfill features whenever a new version of the feature store library is published?
Yeah, of course, we do backfill features. And that's why we still use the historical data that is consolidated by our enterprise data platforms, is to be able to backfill for training. It's not yet very well automated, so this is something also that we're working on for now.
How difficult is it to recalculate things? It's not just clicking a button, right? You need
For
to do
now,
a
it's
bunch of
not.
things.
Yeah, it's not a click of a button, but it's our next iteration, so we're working on that.
Do you often need to do that, or not?
Not yet, because it's been stable so far. We haven't added a lot of features yet, but this is definitely part of our roadmap for the next year, because we want to do a lot of R&D on new features, also on new data models. And when you say new data models, it means new data sources. So this is something that we're actively working on right now to be able to integrate this data more efficiently.
And it's not open source, right? It's internal to Ubisoft.
No.
Do you have any plans to open source it?
Well, if we manage to inner source it, then I would talk about open sourcing.
I guess it's very tightly coupled with the internal platform you have, right? So it's not easy just to take it away and open source. Yeah, that's the issue we have with.
I'd say we could at least outsource the feature part, like the feature library, how we design the feature concept and how it interfaces with Parquet and JSON payload. That part can be easily inner sourced at least. But of course, the connections with the AWS account, with our inner cluster for Spark, that part is not yet ready to be inner sourced, unless you do the same as us.
Oh, did I just? I think I just accidentally marked and answered a question that we didn't cover. Check. Yeah, this one. No. What issues were there with open source solutions like Feast and Hopwork that drove your team to build an in-house solution?
Well, when we started designing our solution, Feast and Hopworks were just starting as well. So we learned a lot by reading about them. But this difference in like having a unique implementation for different data sources, we could not find a way to do that with Feast and Hopworks.
Yeah, all these feature stores are pretty young, right? So they.
Yeah. There's a lot of really good stuff out there. We're constantly, well, the team behind Feast, for example, and the team behind Tecton. We were able to talk with them, and really they're doing awesome things. So I don't know if we're gonna stay with our own internal solution. It's moving a lot. It's moving very quickly. So every month we would have new ideas and new strategies. So definitely we're a super small team around the feature store. So maybe we might be tempted at some point to change and move to something more established. But for me, it wasn't necessarily finding a solution that would work everywhere. It was mostly finding a solution that works for us first, and then being able to understand all the underlying issues that come with the feature store concepts and data engineering around the machine learning product. So it's more about a personal journey of a team rather than finding the solution for feature store across the world.
Yeah, thank you. Where are the Parquet files stored? Do you use any technology to speed up reading or creating, or a technique to reduce the cost of those readings?
They are stored on our internal Spark cluster. So to speed up the readings, I'd say using techniques that are inherent to Parquet files, which are partitioning or even bucketing, checkpointing. So these are mostly the things that we use to speed up our queries.
So you have your HDFS, right?
Yeah.
With Spark. Okay, so you don't use S3 for keeping the Parquet files.
No, so that's why here the fact, like reducing the costs of these readings, we don't have any IO costs like you'd find on a cluster as a service, like on AWS, for example.
Yeah, I guess there is also a trade-off. I guess when you have HDFS, it's faster, but then these machines need to be up and running because they store the data. Right? On the other hand, if you keep them in S3 or some other object storage, then you don't need to machine constantly up and running, but then reading is a bit slower.
Yeah. Yeah, we're leveraging an internal cluster that is used for multiple projects, not only for us. So this is a win-win for us.
How do you handle loading historical data for a newly created feature? Do you find it to be a challenge?
So there are several levels for a newly created feature. We could have a feature that is based on data that exists already. And then at that point, we wouldn't have to worry about loading historical data because the data exists. So that kind of feature is easy enough to create. However, for features that need new kinds of data, or new data sources, or even just new fields that have been added to the upstream data sources, that's where it gets a bit more tricky. So we could rely on some ad hoc scripts for starters to get the data, but for us, in our case, we are trying to find a strategy that that allows us to backfill automatically, be it with a data source that exists already or a data source that we've recently imported. So this is definitely a challenge. This has to be taken into account. But of course, I'd say this difference between if you have the data or not will allow you to define how complex it is to add a new feature. And then if you communicate to your data science team that a feature that already has the data is easy enough to implement, then they would know how much time it would need to implement. And on the other side, if a new data source needs to be added, well, there could be some research time dedicated to go find the new data, to talk to the teams that produce the data, to integrate it and get the accesses to the data, because you also have some data privacy issues at some point. You need to make sure that you have the right to actually access the data. So all of that needs a bit more discussion, and that goes back to a regular, I'd say, R&D process around the creation of a new feature.
Yeah, thank you. It seems we do not have any more questions. Do you want to say anything else before we finish?
Well, yeah, just thank you so much for inviting me. I hope it was interesting for everybody, and yeah,
it was.
Awesome.
Yeah, thanks.
Well, I'm glad. Thank you so much.
Somebody has questions. What's the best way to reach out to you?
Well, you can reach out to me on LinkedIn. My name is Jeanine Harb, as in the description. So yeah, definitely reach out to me, and I'm available if you have any more questions around the feature store. I'd be happy to answer your questions.
Yeah, thanks a lot. Thanks again for joining us today, for sharing your expertise and experience with us. So yeah, thanks everyone for joining us today, also for asking questions, for watching. Yeah, have a great week, everyone.
Thank you, everybody.